Okay.
Yeah.
Now it's recording.
When you
So
we finish, you can press it again.
I see.
I
see.
Convince people that using symmetrized bases was going to make the difference in calculation precision people care about.
I think that's like he says the initial comments were like, it seems like the concept would do this.
That's right.
You can ask that.
Yeah, that's right. No, that's right. It's always funny, right? If an undergraduate, if you come up with a theory paper that an undergraduate should do, you submit it to Nature. Right? Because that means that it's that good. So one of my favorite stories about that is the no cloning theorem in quantum mechanics. Bill Wooters and Zurek went up to Wheeler and said, should we even publish this? And he said, yes, Nature. It's a three-line proof. Okay. Yeah, so I believe in it.
The medal's going to go directly to the quote.
Yeah, that's right.
Maybe even Marshall American University.
That's right. Fully support. Good. Oh, did I just take your seat?
It should be more accurate.
You miscalculated. If anybody's interested, on Saturday, I think there's a group going to Bainbridge Island. It's a 35-minute ferry ride from downtown. So if you're interested, just let me know.
When do we leave? Saturday?
I was thinking 9:35.
Saturday morning?
Yeah.
And you go to an island?
Yeah, Bainbridge Island.
I'm interested.
Okay.
So.
Okay. So today, Professor Wei Zhang will talk about from Renmin University of China. We'll talk about exotic pairing states in 2D Fermi gases with the spin orbit coupling.
Okay, so first I'd like to thank the organizers for giving me the chance. And so this is the title of my talk. And usually the title ends up here, but because this is a field body event, so I add a subtitle here. And there will be an additional part I just finished yesterday, addressing this connection from the many-body physics to the field body physics. And I come from the Renmin University of China, and please allow me to use 1 minute to give a brief introduction. So Renmin University of China, if you translate literally, it's called People's University of China. So it's, as you can tell from the homepage of the university, it's actually a liberal and art college. So we have these beautiful girls. And this university is founded in 1930s by the Chinese Communist Party during the Long March. So the main purpose at that time is to teach Marxism to the party members. But right now we moved from Marxism to more subjects. So we have a huge department of humanity and social science, a very good business school and law school. And starting from 2005, they decided to build a physics department at the university. I think the president wants to have more male students to balance the ratio between the dominance of female students in the school. But I don't know what's his original purpose. That's my guess. So right now we have about 30 faculty members in both condensed matter, experimental and theory, AMO only in theory, and particle and cosmology in theory, and material science and engineering. And the final thing I would like to address is that we have still about 10 to 12 something faculty positions opening at all levels. So if you have a postdoc or students want to find a job, then that's an opportunity. And then I will acknowledge my collaborators and students. So the work I'm going to talk about today is mainly in collaboration with my student Wei Zhang from Renmin University and my colleague Peng Zhang, and also Professor Wei Yi from USDC. And both Peng Zhang and Wei Yi will go to this program, but in a late stage, probably the end of April. So if you still hanging around at that time, you can discuss with them as well. And also I thank NSFC and the Ministry of Education for funding support. Okay, so this is the outline of my talk because I don't think everyone in this room are very familiar with the concept of spin-orbit coupling in cold atoms. So I will give a brief introduction about what it is and how to realize it in neutral atoms, and then the effect to the single particle property. And then I will move to the second part to discuss some exotic pairing states in 2D Fermi gas with Rashba spin-orbit coupling and effective magnetic fields. So I will show you that the most interesting part of this system is that we have a topological superfluid in this system, and we have FFLO pairing within a single branch. And if you combine this together, we have a topological FFLO state, which is quite exotic. And finally, I will discuss the field body physics from a many-body perspective. I will try to answer these two questions. So what is the difference between quasi-2D and the true 2D, which means that when and how the third dimension matters. And then finally, I will raise up, instead of answering a question, is about the validity of a contact interaction. Okay, so let's go to the first part. Spin-orbit coupling is well observed in nature. So the most known example is that the motion, the spin of the moon and its orbital motion around the Earth. So the moon is completely locked by the tidal force of the Earth. So the only side of the moon we can see is this side. So we can only see that. We cannot see the back of the moon. So in the Eastern culture, we think the pattern on the moon is a toad and a rabbit. Well, in some Western countries, they think this is only a rabbit. So, but there is always a rabbit on the moon. It's quite universal. I don't know anybody who investigate that. And in a continuous system, because the orbital is r cross p, but in a continuum system, the r doesn't mean anything if you have translational symmetry. So the spin-orbit coupling in condensed matter community, we usually think about it as a spin momentum correlation or spin momentum coupling. So if you write it in a quite general way, it's something like this. So sigma x dot kx with some coefficients, and sigma y ky and sigma z kz with probably different coefficients.
Can you have a sigma x times ky or something?
Yeah, but you can always rotate that with some spin rotation. Yeah, in principle, yes, you can have that. Yeah. So if you choose different combinations of these coefficients, alpha x, alpha y, and alpha z, you can have different terminology of the spin-orbit coupling. For example, if everything is equal, then you have a three-dimensional isotropic spin-orbit coupling. And if you have choose alpha z equal to 0 and alpha x equal to alpha y, you have a spin-orbit coupling which is isotropic in the plane, but there is no spin orbit coupling along the z direction. We call it Rashba spin orbit coupling. And then if alpha x equal to minus alpha y, we call it Dresselhaus. And then finally, if both alpha y and alpha z goes to 0, you essentially have a one-dimensional spin orbit coupling. Or you can see this case is just an equal combination of the Rashba and the Dresselhaus. So it's also been referred as equal Rashba and Dresselhaus spin orbit coupling. Okay, so now we go to the experimental realization of this ERD spin orbit coupling in cold atoms. It's first realized in NIST at the Ian Spellman's group. So what they did is that they have a BC of atoms, and then you put two counter-propagating laser beams. So and then you have a two-level system. Then the atom in a pseudo spin up can absorb a photon of red to upper stage, and then emit a photon of blue, and then go to this pseudo spin down state. But by doing that, the atom will gain a net linear momentum of 2k by doing this. So the Hamiltonian of this transition can be written like this. So you can see there's e to the I2k0x on the off-diagonal terms. And then you can do a unitary transformation of this Hamiltonian, and then finally you get an effective Hamiltonian like this. So then you use the Pauli matrices to rewrite this effective Hamiltonian into the form like this. As you can see, now you have the linear momentum kx plus k0 is a constant, and times the spin, the Pauli matrices, and then you have square. And if you open this square, then you can see the kx and the sigma z will couple to each other. And that's how they realize this spin momentum coupling. But this form is not equal to the form I showed you before, because this is kx dot sigma z. So you make a simple spin rotation along the y-axis, and then you have this form. And in this effective Hamiltonian, you can see this is the one-dimensional or equal Rashba and Dresselhaus spin orbit coupling. Sorry, I missed a k0 here. There should be 2 k0 sigma x kx. And in addition to that, this big capital omega over 2 is the effective Zeeman field along the z direction. And the capital omega is the Rabi frequency of this two-photon process. And this little h is an effective Zeeman field along the x direction. And the h is the two-photon detuning of the two-photon process. So now we try to understand the single particle physics of this effective Hamiltonian. The single particle dispersion, if there is no spin orbit coupling, it's just a simple parabola. And then you add in the spin orbit coupling, the one-dimensional spin orbit coupling, you can see that the parabola divided into two, and with the minimum located at a finite momentum, not at k0 anymore. And now, if you add in the effective Zeeman field along the z field, which corresponds to the Rabi frequency of this two-photon process, then there will be a gap open at k equal to 0. So in this case, when there's no magnetic field, this red branch and this pink branch are touched at k equal to 0. But if you add an additional magnetic field, there is a gap will open at k equal to 0. Okay? And then if you add in another effective magnetic field along the x direction, then the single particle dispersion will be tilted, so that the veil here and the veil here are not equal anymore. So that's the single particle dispersion. In experiment, people have used the same scheme to Fermi gases as well. and they do observe the single particle dispersion changing from a single parabola to a double parabola, as you can see from this experiment. The experiments was done by both Shanxi University at Taiyuan, China, and MIT in Martin Weyland's group. So yep, that's this. That's the introduction to the background. And right now, the experiments, I have to say that the experiments only realize the 1D spin-orbit coupling in this case. But as a theorist, I could be more ambitious. So I'd like to talk about the more interesting, theoretically more interesting, the rush-bar spin-orbit coupling case. And I'd like to say that there is some theoretical proposals to how to realize a rush-bar spin-orbit coupling in experiments. But as far as I know, there is no realization at this moment. There's always some technical issues. So now I move to the second part of my talk. Yes? Sorry. Okay, the second part of my talk about the 2D Fermi gas with rush-bar spin-orbit coupling and B field. So before I begin, I have to let you know the configurations in my head. So we have a two-dimensional homogeneous Fermi systems, and that is my xy plane. And the rush-bar spin-orbit coupling is within this plane. So it's isotropic two-dimensional spin-orbit coupling. And then the magnetic field can be either pointing along the z direction, which is out of the plane, or pointing along the x direction, which is in the plane. So we will discuss both the out of plane case and the in plane case. Okay. So yes, let's go back to this single particle dispersion. As I discussed before, when there is no spin-orbit coupling and no Zeeman field, it's just a simple parabola. So there's an inversion symmetry and there's a time reversal symmetry of this system. Inversion symmetry means that if you change from k to minus k, then nothing changes. And the time reversal symmetry means the spin up and spin down are degenerate. So we always have these two kind of symmetries. But if you apply a rush-bar spin-orbit coupling, but no magnetic field, then the dispersion will change to this form. The energy minimum will become a circle in the momentum plane. Okay, and in this time we don't have inversion symmetry anymore. This is because the spin state on this point will be pointing along the positive k direction, while the spin on the minus k direction, on this point, will pointing along the minus k direction. So the k and the minus k single particle states are no longer equal to each other. So there's no inversion symmetry anymore. Yes?
So this inversion symmetry, you define it by k to minus k?
Yeah.
But then it's not a discrete symmetry, right?
It's not a discrete.
Just a rotation by 180 degrees.
What do you mean a rotation by? Inversion is not a rotation by 180 degrees.
In 2D people usually define discrete parity or inversion by reflecting just one component.
No, it's a reflection of everything.
But then it's not a discrete symmetry, right? It's just a part of the rotation. So in 3D, if you split all the components, then it's just you cannot obtain it by rotation. But in 2D, you can obtain it by rotation.
And what's the consequence of that if it's not? So you're saying that this inversion symmetry, it's a subgroup.
Yeah.
Of the rotation.
So
Yeah,
I thought that it's kind of so time reversal is a discrete symmetry, right? So inversion.
But what would be the consequences if it's discrete instead of continuous? Is there physical consequence of that?
Usually split right into the continuous apart, and then you should describe discrete apart, which cannot be obtained by continuous ones.
I mean, even if it's a subgroup of the rotation, or an element that is a subgroup of the rotation group, it's still typically called a discrete. Like if we just include inversion, it is still a discrete transformation.
No, it is, but technically, you don't do it in 2D because it doesn't make sense. So it's superfluous to do it. It doesn't give you any additional information, physical insight, or anything else. So you can do that, but it doesn't do anything. You can do C3, for example, the same way, but it doesn't give you anything if you have full rotation symmetry.
Yeah. What I mean here is that you change from k to minus k. You only do that in momentum space, but not do any rotation in spin space. Then the state here is not equal to state right there because the spin are pointing on the opposite direction. That's the only thing I mean here. Okay, so that's the difference from the case without spin orbit coupling. Okay.
And that means it's perfect to do S pairing in this case, correct?
Yes. Yes. And so now if we add in a Zeeman field along the z direction, then both the inversion symmetry and time reversal symmetry are broken. So we will keep in mind of that. So we'll see, even in the single particle dispersion, the system is already interesting because right now we can realize something called Lifshitz transition in this system. The Lifshitz transition in condensed matter is a term in condensed matter physics. Is that when you change the chemical potential, the Fermi surface will undergo a topological change. So as you can see in this system, when you increase the chemical potential, at first you have two Fermi surfaces, corresponds to one single branch. And then if the Fermi surface is lying between within the gap, then you have only one Fermi surface. And then if you raise the chemical potential again, you have two Fermi surfaces, but each one corresponds to different single particle branch.
In practice, how big is the density? You see the gas density you see in the first case there, because the chemical potential is very low, so the density is probably very low.
Well, it all depends on how large the magnetic field is.
I
Yes.
understand, but
Yes.
how large magnetic fields you can have? You can have 100 Gauss or something like that, probably. Not a Tesla. Right?
Well,
so I'm wondering, you see, if you're going to make experiments, how reasonable is to discuss one of these states, because they might be out of reach.
well, it's quite you cannot translate that thing into Tesla because here the interparticle distance is very large, so the Fermi energy is very low comparing to the condensed matter systems. So I would say it's quite doable because experimentally people see this Lifshitz transition already.
So
yes.
they can study, for example, this system.
Yes, they can start from here and then go to here and they do that.
For example, the pairing gap is reasonable.
No, because the temperature is not low enough.
But how it compares with the Fermi energy pairing gap there?
What? Excuse me?
The pairing gap, how it compares with the Fermi energy?
The pairing gap depends on the interaction. Usually it's about 0.1 Fermi energy, something like that.
Too small.
Yeah.
I thought you said that there were no experiments on Rashba spin orbit coupling.
But on NIST spin orbit coupling, they see this change.
Okay.
Okay. Yeah. So they from two. Well, in NIST, in the ERD spin orbit coupling, they have two wells. They have one, and they can see the Fermi energy just touch the lower branch only, and then the gap, and then the upper branch. They do see that.
But I think all these experiments to date, they're just a few Gauss, right? Because they're looking at very small Zeeman experiments, I thought.
Well, I haven't translated that term into Gauss because first it's the Rabi frequency, right? The magnetic field is the Rabi frequency of this lambda transition.
You're talking about the kind of artificial magnetic field, whereas I'm talking about the real magnetic field in the experiment that creates the Zeeman structure. I thought that's what you were asking.
I'm interested in how you create a splitting. You see, if you create this real magnetic field, then
it's not a real magnetic field. It's
same magnetic field.
Well,
so
it is a real magnetic field that made the energy levels that are addressed, right? But then, in addition, there is a
no. It is this magnetic field. It's the Rabi frequency. That opens the gap.
Effective magnetic field.
Yeah, it's an effective magnetic field. It's not
a
a real
magnetic field in the problem too that made the energy level spacing.
Yes.
That is being Raman coupled.
Yes, but this is not the one I'm discussing here.
Is the real magnetic field responsible for the term for the coefficient H?
This one? Well, it will affect this one, but it also depends on the lasers. Yeah. So yeah, the Zeeman field I was always talking about is actually this one. It's the Rabi frequency. So it's an effective magnetic field.
But here you have a mixture between what called Rashba and Dresselhaus spin orbit, right?
Yes.
Because
Yeah, well, yeah, so of course, yeah. In the Rashba case, then it depends on the experimental scheme, how to realize that. So that may be different. Yes.
And in this MIT experiment, they created this type of situation?
Yes.
Yes, okay.
Yes.
Thank you.
You're welcome. Okay, so let's do to this one. Okay, now we add in the interaction. And when there's no spin orbit coupling of Zeeman field, the spin up on this side of the Fermi surface will pair spin down on this side of the Fermi surface. And this is called the BCS pairing. And the resulting Cooper pair will have a zero center of mass momentum. And then if we have no spin orbit coupling, but we apply a Zeeman field, then spin up and spin down is not equal to each other. The time reversal symmetry is broken. So if we still want to pair spin up and spin down along on the Fermi surface, then the resulting Cooper pair will acquire a finite center of mass momentum. And it is called the Folder-Ferro-Lakin-Ovchinnikov pairing, or so it's usually referred as FFLO or LOFF state. Yes?
In your picture, are you making an assumption about the interaction? I mean, are you assuming it to be weak and attractive?
Yes. This picture is weak.
Conservative picture or mean picture?
This picture is only is weak, because if the interaction is strong enough, then you don't have Fermi surface anymore. So nothing makes sense anymore. So yeah. So this picture is weakly interacting picture. Okay. Attractive. Yes. Yeah. Right. So, but the FFLO pairing states will have a finite center of mass momentum, so it contains some finite kinetic energy. When this kinetic energy is larger than the condensation energy, which can be gained from the pairing, then the FFL pairing is not stable anymore. That is why the magnetic field is always detrimental to superconductivity. But if we have spin orbit coupling, then the story can be changed dramatically. If we have spin orbit coupling and Zeeman fields, then as you can see, every single state is a mixture of spin up and spin down, because spin is no longer a good quantum number. So it is always possible to pair the spin up component on this side to the spin down component on the other side. And we call it the single branch BCS pairing. Usually the BCS pairing requires two branches of the Fermi surface. Yes?
You have this spin orbit coupling by how much this Fermi momentum changes. I mean, if you have the simple parabola, you're crossing
yes.
the given chemical potential at 1 kF, but now you enlarge this parabola by adding, you see this bump in the middle, and kF will be modified, right?
This bump in the middle? That depends on this K0.
That's what I'm asking. You see, by how much you modify the position of the Fermi surface when you add the spin orbit. Because if you don't have the spin orbit, you have one parabola which will cross the horizontal line at one point.
Yes.
Adding that, you move them up like this, and then the lower one will cross the. You see the.
Well, even the lower one cross the Fermi surface, it doesn't matter. It still
No,
still
but I'm
holds.
interested by how much you change the Fermi momentum, because that will influence the density of states too, right?
Yeah, but that's only quantitatively. I don't have that answer right now. That's a simple answer.
Density
Yeah.
of states and the exponent in BCS gap, so that could be quite a bit.
But it will depend on the feeding factor. Everything depends on, and you can still tune that. You can open the gap by increasing the effective magnetic field, or something like that. Yeah. Okay. So actually, it's if the chemical potential is large, so that two Fermi surface, two branches are crossed, then the pairing scenario possibilities can be even more. You can have inter-branch pairing, you can have inter-branch pairing, and you can have all these possibilities. So that then the system can be very complicated. Okay. And another very interesting possibility here is the presence of a topological superfluid. The topological superfluid, of course, it is a superfluid phase, and it's fully gapped in the bulk. And it also has some non-trivial topological properties, including there is a topologically protected gapless edge mode. Actually, it's protected by the particle hole symmetry. And it will have a Majorana fermions if we create vortex within the system. And these Majorana fermions are believed to be valuable resources for fault-tolerant quantum computing. So we are interested about this type of superfluid. The first, it is believed that this kind of topological superfluid can be realized in a px plus IPY superconductivity. But px plus IPY superconductors, we haven't found any real systems that can stabilize such kind of superconductivity.
What's the picture there below? You see with the contours and so on?
This one?
Yeah.
This one is this is a vortex, and let me see. This is a vortex, and in the center, in the vortex core, there could be Majorana fermions, and these blue lines indicates the gapless edge mode on the boundary.
Do you consider different shapes of this?
No, it doesn't depend on the shapes.
No, because the size of the circumference depends on the shape.
That's
the reason I'm asking. You see,
the size of
maximize, because if you take a circle, you minimize the area for given circumference. Maximize the area. I'm sorry, for given circumference.
You mean the shape of the sample or something?
Yeah, because it could be circular, it could be, you see, the rectangular, it could be square, you see, and then the number of states there is different.
But the edge mode doesn't depend on the shape.
The number of edge states will depend.
No, it won't. Just
well,
two.
By making the size of the universe, obviously, it will have more states on the edge.
No, there were only two.
Yeah, only two?
Only two, yeah. One is propagating this way, the other one is the other way.
So it's like in the case of a vortex, you have only
Yes,
one.
yes. Okay. That's what we call it topologically protected. And then you can have disorders on the surface boundary. It doesn't matter, it's just there. Yes.
Okay.
Yeah. And in 2010, Jay Shaw and his collaborator proved that you can actually realize a topological superfluid in a two-dimensional Fermi surface system, which breaks inversion and time reversal symmetries. Actually, they find that. So we can see these keywords: two-dimensional Fermi system, breaks inversion and time reversal symmetries. That is exactly what we have for a 2D Fermi gas with Rashba spin orbit coupling.
So this inversion is the one?
Yes, this is the one I was. Yes. So yeah, this is the slides you have already seen. So this is the case we are interested in. So in order to, then it is an interesting question to see, how can we realize that in these systems? So what we do is we use this Hamiltonian. You have a non-interacting part spin orbit spin orbit coupling and the contact interaction Hamiltonian, and then you use a mean field approach to write down the thermodynamic potential, and we then determine the phases by minimize the thermodynamic potential. The advantage of this approach is that we can guarantee that the ground state we obtain is the true ground state, but not some metastable states. Okay.
Couples in the z direction, right? The spins.
This one?
Yeah,
No.
spin up,
No.
spin down.
No, it's you it's on the off-diagonal term, so it's sigma x. So you destroy a down and it create a up, so it's off-diagonal.
Also, you have only sigma x here.
Yes.
You don't have the two of them.
Uh,
You don't have either. You have a mixture.
sorry. Let me see.
And then you should have.
No, you have both because you have a e to the minus I phi k here. So you plus k to the e to the minus I phi k, you can actually have kx plus iky.
Okay.
Yeah. So it's that's a Rashba. Yeah. Yeah.
So you can write it.
Yes. I just make sure I didn't copy from different papers. Yeah. So yeah, this is Rashba.
Okay.
K is a scalar up front? Or
Yes, k is a scalar.
Then you have
What
the
is
angle.
phi k?
Phi k is the angle between k to the x direction. Sorry.
I think it works out, you see, because you write it in the complex form.
Oh,
vector.
okay. I see.
Right. So this is kx. This is ky. So this is the k, and this is phi k. Okay. Yeah. So
Part
yeah.
of it is kx minus iky.
Yes.
Yeah.
Yes.
Okay.
Yeah. Okay. So here I show a typical phase diagram we obtained. And let me see, the x-axis, alpha is the intensity of spin-orbit coupling, kh just some unit, and h is the effective Zeeman field along the z direction. Right here, I only consider the field along the z direction. Okay, so h is that field. So on this phase diagram, the left-hand side is the small spin-orbit coupling or large magnetic field limit, and the right-hand side is the large spin-orbit coupling or small magnetic field limit. And the vertical axis is chemical potential over h. I always choose h as the energy unit. And the reason I plot the phase diagram like this is that in the local density approximation, if you write down a vertical curve from somewhere on the phase diagram to the bottom of the phase diagram, then the phases you see by going down from this curve, from this line, is the phases you will encounter when you move from the trap center to the trap edge. Okay. So the most
What's VA?
VA is vacuum.
Oh, vacuum.
Vacuum, yes. Yeah. So on this phase diagram, the most intriguing feature is that there is a topological superfluid phase in a fairly large parameter region. And it is separated from the conventional superfluid phase either by a second-order phase transition line or a first-order phase transition line.
In order to have these edge states, you need a finite sample.
You need a finite sample,
And
yes.
then the formula you wrote for the infinite sample.
Yes.
So can you be more specific now? How
Well, you can understand this one as a.
So it's a discrete sum there.
You can consider that as a finite sample with a periodic boundary condition.
So this is what you've done.
Yes.
Correct.
Yes.
Right?
Yeah. So we have a quantization volume here. So.
Okay. And
Yes.
you see the surface should play a role when you calculate the thermodynamic potential, because in not proportional to the volume, you'll have a surface then too. So.
No, you have that effect, but that effect will be negligible when you have a large enough sample.
Well, then the edge states you see are negligible too. So how do you see them?
No, negligible. No, the edge state effect to the whole sample is negligible, but the edge state is always there.
So how you distinguish the two states by looking at the thermodynamic potential?
From this one?
Yeah.
No, you cannot see the edge state from this one. What you need to do is you need to do some local calculations, such as Boglie-Wolff the run or something.
The phase diagram then.
The phase diagram is determined by this homogeneous system.
But you don't see the topological superfluid there because you have the surface. You see,
Ah, I
this is the
see.
problem.
Your question is that how can I determine this is actually a topological one?
Yes, from
Okay.
looking at the grand canonical potential, you see
Oh,
which is
yes,
the
yes,
volume.
yes,
You
yes,
don't have the
yes.
surface
Yes. You don't need you don't need to see the edge states to determine this is topological. You can calculate the topological numbers, such as the Chen number. You can calculate that. The Chen number addresses the topological nature of any states. It is 0 for a conventional superfluid phase, and it is 1 plus or minus 1 for a topological one. And when you cross the phase boundary,
measurable?
It's measurable.
How?
Chen number. How do you measure Chen number?
Because if this is a new superfluid, I have to measure it.
Okay.
I have to look at that and see that it's blue, it's not green.
Okay.
How do I do that?
Okay. Chen number, you cannot directly measure Chen number, but there is a proof that you can relate Chen number to the presence and the number of edge states. So experimentally,
see those then?
well, that's a quite long proof. I mean, but there is.
No, how do I see them in experiment?
The edge state?
Yep.
The edge state, you can see experiment like a spin quantum Hall or something like that. You can do experiments.
Isn't it related to Hall conductivity?
Yes, it is related. Yeah. It is
I
related.
don't believe that. But anyway.
Just
First of all, it's only 2 electron states. In a big sample, we have 10 to the 23 particles. Right? So how are you going to see the effect of 2 particles there? No, Hall effect, you see, it's not such a small number. It's a big number. It's macroscopic. This is not microscopic.
Yes,
This is
yes.
microscopic, and well, there's a macroscopic effect. So you cannot see that way. So I don't understand that.
Yeah, we can discuss later about this. Or we can keep agree or disagree at this moment.
It's not easy. If it's a new superfluid, you should see it. It's blue or green. You see how we can measure it. If it's a superfluid, it really has its superfluid properties. So I have to know
Maybe we
this.
can keep the discussion for the
Yeah.
Well,
Okay.
There's the physics of it. You see, there's the main physics here.
Yeah.
Could I ask something?
Yeah, sure.
So in usual Px plus Py, I think it's kind of reverse. So at positive chemical potential, you have topological one, and at negative, you have.
For Px plus IPy, then what?
Spinless fermions, for example. You
For
have
spinless
topological
fermions?
BCS phase. And non-topological is BC because it's connected to vacuum. So in your case, it's kind of interesting because you have it's reversed.
Right. Well, this can be understood very easily because you need the chemical potential to be low enough such that you don't compromise with the upper branch. Because if you pairing within 2 branches, then you don't have this topological nature. So the picture is basically like this. So the spin on the lower branch is rotating like this, and the upper branch is rotating counterclockwise. So if you populate both branches, then they will cancel each other. You have to contain yourself to the lower branch so that you have this nature. Yes. Okay, and then we we calculate the phase diagram by increasing interaction from the BCS limit to the BEC limit. As you can see, the region for topological superfluid gets smaller and smaller and eventually disappear in the BEC limit. This is what we expected because in the BEC limit, the 2 fermions are strongly paired into bosons, and all topological natures are just buried within this internal degree of freedom. Unitarity, well, that's hard to define because it's 2D. So we use the binding energy, 2-body binding energy as a signature. There's no unitarity in 2D. Okay, and then we go back to this phase diagram and you see there is another interesting feature is that there is no normal phase on this phase diagram. And we know this is not the case when there is no spin orbit coupling. But this is, we can explain that by this hand waving argument that I have showed you before, that you can always pair the spin up component to the spin down component here. But this is only a mean field calculation. So the naive question is that do we still have this pairing instability for arbitrarily high magnetic field if we go beyond mean field? And to answer that question, we so yeah, this is the question I raised. What actually happens here? So to answer this question, we go beyond mean field and we incorporate the first order particle hole fluctuations, and we discuss the pairing physics at large magnetic field limit. So right here. And at this point, we find a pole-around to molecule transition, which suggests that the system is actually a normal gas in this limit. But we cannot determine the exact phase boundary here. But all we can get is that if you increase the magnetic field high enough, eventually you will have a normal gas. So that's
the mean field gives you a wrong phase diagram, basically what you're saying.
Well, it depends on how you define wrong. I mean, quantitatively, I would say I won't trust mean field in the 2D systems, but it can give us very useful qualitative signature of that. Qualitatively, it's trustable, I think, I would say. Yeah. Okay, and so then now we, go to the case when we add the X magnetic field. Okay, so now we have two magnetic fields. One is out of plane, the other one is in the plane. And we have a 2D system. Okay, in that case, the Fermi surface is tilted. So this well is deeper than this well. And then if you still want to pair fermions on the Fermi surface, then the resulting Cooper pair will always have a finite center of mass momentum. It's just because the Fermi surface is not symmetric anymore. And in this case, we can actually show that the BCS pairing becomes unstable. And this is because the SOC induced the spin mixing and the in-plane field induced the Fermi surface asymmetry. You can actually prove that in the weak coupling limit. And because of this, the pairing scenario will be more complicated. So I don't even want to bother you with this figure. I just show you this. This is complicated. And the resulting phase diagram will be determined by the competition or coexistence of these possibilities. Just flash you the mean field phase diagram for this case, for the with spin orbit coupling, a Z field and an X field. And this one, as a comparison, is the old phase diagram with spin orbit coupling and Z field, but no in-plane fields. So as you can see, when you add the X magnetic field, then all BCS phases on this phase diagram are changed to some FFLO phase on this phase diagram. BCS is not stable anymore. And specifically, the topological superfluid phase is changed to a topological FFLO phase on this phase diagram.
So what's GFF and NFF?
Okay, GFF, NFF. GFF is gapped. It's fully gapped in the quasi-particle dispersion. NFF has nodes in the momentum plane. And the mixed here is some coexistence of different FF states.
Gap is a direct gap, or it could be indirect gap?
Both. It could be indirect. Yes. Okay. And yeah. So this the topological FF state can be understood in this way. The topological superfluid phase is fully gapped in the bulk, and the topological nature of this phase is protected by the gap. So you can consider the X direction magnetic field as a perturbation to the system. As long as this perturbation is not strong enough to close the bulk gap, then the topological nature is still maintained. So that's the topological property of the FF phase comes from. And we also calculate the momentum distribution of the minority fermions, and we find that there is a qualitative difference between topologically non-trivial and topologically trivial states. Well, that may answer your question. So how you see the difference. For a topologically non-trivial phase, the momentum distribution has a dip around the origin, But for the trivial case, you have a peak around the origin. So that's, if we eventually realize, experimentally realize this kind of system, we can use that as a detection method. So now let me summarize the well, time goes fast. So yeah, I discussed the many-body properties of a two-dimensional Fermi gas with Rashba spin-orbit coupling. When there's a Z magnetic field, we have a topological superfluid. And we also discussed the pairing instability at large magnetic field. For cross magnetic fields, then the BCS pairing is no longer stable, and we have a topological FFL O phase. So now, usually my talk ends up here. But since this is a few-body events, I will go to this few-body physics. I will make it quick. So as you can see, all these interesting things happens in 2D. What I investigate is a 2D model. So, but in real life cold atom experiments, we never have a true 2D system. All we can do is we push the system along the Z direction and confine it very strongly so that you can see this confinement is larger than any energy scale of the system. And then we see this is actually a 2D system. So usually the trapping potential along the Z direction is 10 to the 4, 10 to the 5 hertz. And the trap size is 10 to the minus 7 meters. And the particle separation within this 2D plane is 10 to the 6 meters. So it's about micron. So this is one order of magnitude smaller. You can think, well, this is quite 2D enough. But there is another length scale, which is the interatomic potential range, which is in the scale of nanometers. So, well, when the two particles in this quasi-2D configuration are far apart, you can see this quite 2D. But when they actually interact, so they are within this interatomic potential range, then the 2D nature, 2D property actually breaks down. So instead of the two particles interact instead of this way, they actually interact in this way. So when they do interact, they don't see the trap anymore. And then it requires us to find a way to incorporate what happens here. What we do is that we first discuss a two-body bound state in a quasi-2D geometry. So in the Hamiltonian, we have the non-interacting part, the spin-orbit coupled part, the boson-Fermi conversion part. We use a two-channel model, and there's an interacting part. In the non-interacting part, we have this trapping potential along the Z direction, and we use this two-body wave function. And to solve that, we can have the two-body bound state, okay, at center of mass momentum 0. At center of mass momentum 0, the two-body bound state binding energy increase from the BCS limit to the BEC limit. And when you see when there's no spin-orbit coupling, the binding energy can become comparable or even exceeds the trapping frequency. So as you can see, -1 is the trapping frequency. Okay, so that can be, the binding energy can be quite larger than that. And when you add spin-orbit coupling, it actually pushes the binding energy even downwards, so that the binding energy becomes comparable or exceeds the trapping energy, even on the BCS side of the Feshbach resonance. Mm-hmm.
Can you say what units you're using for your binding energy?
H bar omega Z.
And then what you said something about -1. So you're measuring
-1 H. Yeah. So what I plot is minus binding energy.
So the total, you mean the real energy?
Well, yeah. Okay. Well, because binding energy, people you sometimes define as a negative number, or sometimes define as a positive number. Always positive number. Okay.
This is
yeah.
the real energy.
Yeah. So this is a minus absolute value of binding energy. That will be secure, quite secure.
This is in the relative degree of freedom, and you've subtracted.
Yeah. I subtract every energy threshold. Yeah. So the threshold is 0.
So this is the energy with respect to the 0 point energy.
Yes.
That's what you're calling bind.
Yes.
Bind
Yes.
with respect to the 0
Yes.
point energy.
Yes. Not from the 0 point energy, because when you have spin orbit coupling, the threshold is not 0 point energy. So I scale from the threshold. Okay, that's what I mean.
And so what's AT and AS again?
AT is the length scale of the trap. AS is a 3-dimensional S-wave scattering length.
So why is it bound even if the spin orbit coupling is switched?
Because it's quasi 2D. So when you have a trap along the direction, then you always have a bound state.
Can you explain it intuitively?
Intuitively, well, yes, because for example, at unitarity, why there's no bound state in 3 dimension? Because this is because there's no length scale, and there's no energy scale. The only length scale is AS, but that diverges. So, but if you have a trap, then you have an energy scale here. Then everything will scale up with this h bar omega z, including the binding energy.
How does it explain? So if you go to
This way?
limit, what is the form of the dependence?
I don't remember.
Exponentially small.
Exponentially small?
Yeah, that's
Yes.
true.
But this is not 2D, it's 3D, it's quasi 2D.
Yeah.
But if you have weaker tracking ratio, then you do have
Well,
this
but
shadow.
when the scattering lane becomes comparable with the width of the sample, then it's 3D problem. So you don't have exponential.
But
binding
AT
energy.
equals
On that
0.
side, when
AT
the
equals
scattering is
0
more negative.
is
That's at -1.
true 2D, isn't it? Isn't that
No,
what
no,
you're
no.
comparing?
AT goes to AT. Yes, AT goes to 0 to true 2D. Yes, 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 yes.
Bound state at that point.
You have the bound state.
Because that's 3D order.
On that side,
Yes,
AT
it's
is
3D
more
order.
negative. You do have bound state.
Yeah. Okay. What I focus is not goes to infinity anyway. So as you can see, if you add spin orbit coupling, the binding energy actually gets increased, and that's the main point here. So if we calculate the fraction of atoms on the true 2D ground state, then you can see it decreases from 1 and then goes to some number less than 1 in the BEC limit. So that tells us that in the BEC limit, or even at the unitarity, the system is no longer 2-dimensional. You have to incorporate the degrees of freedom on the excited states. Because you can see there is a more and more important contribution from the excited states fraction. And this is for the case without spin orbit coupling.
Excuse me, you have a 2-channel model.
Yes,
Right?
yes.
Doesn't that mean that
No, the Feshbach molecule is here. It's always small. It's red Feshbach resonance.
so it doesn't depend on what you assume for the coupling between your 2 channels?
No, if you write it in AT over AS, as long as it's a white Feshbach resonance, then everything has a
Okay,
universal
so
behavior.
You are looking at the white
Yes, yes,
resonance.
yes, yes.
Thanks.
So what are these integers? 0, 0, 1, 1?
0, 0 means that you have 2 atoms, and both of them reside on the ground state of the transverse degrees of freedom. Okay. And when there's spin orbit coupling, you can see the ground state fraction decreased from this no spin orbit coupling case, and which means that the excited state is more important. That is understandable because when you have spin orbit coupling, you actually increase the binding energy, and that makes your quasi 2D approximation worse. Okay, so from this calculation, I think I can answer a few questions. First is that quasi 2D Fermi gas can be looked as 2D. The answer is only on the BCS side.
So you're still considering Rashba coupling?
Yes, yes. And what if we introduce Rashba spin orbit coupling? Okay, this is the answer. And actually, it makes things worse because that will increase the two-body binding energy. And then the question is, can we still simulate 2D physics with a quasi 2D system? And the answer is yes, but we need another way. The other way is like this. We categorize the degrees of freedom in this quasi-2D model into 3 classes. The first one is fermions in the ground state, and the second one is the fermions in the excited states, and the third one is the Feshbach molecules. As you can see, these fermions in the excited states and the Feshbach molecules has very large energy scale and very short length scale. So if we want only interested in the low energy physics or long distance physics in the system, we don't actually care what happens within such a small length scale or such a high energy scale. So what we can do is that we can group the bottom 2 category of degrees of freedom into dressed molecules, and which is structureless bosons. And then we write down an effective 2-dimensional Hamiltonian in a 2-channel model form, where the 2D fermions, which is essentially the fermions in the ground state, assumes the open channel, while the dressed molecules assumes the closed channel. And
boson have any spin?
No, no.
It's a spin singlet?
It's a spin singlet, yes. Yeah. So this is a phenomenological model. I write it here, and it with some free parameters we need to fix. And how we fix that? We fix that by matching the single particle physics and the 2-particle physics. The single particle physics includes the single particle dispersion, and 2-particle physics includes we fix the background scattering, the 2-body binding energy at a given detuning, and the number of fermions in the ground state at that detuning. So the bottom 2 matching conditions translates to we'll fix the singular point of the T matrix and the first derivative of 1/T at the singular point. And if you use the many-body T matrix language, then this effective Hamiltonian can mimic the original Hamiltonian as long as the chemical potential, the fermionic chemical potential, is not very far from 1/2 of the binding energy. Okay. I think here the binding energy is the negative number. So yeah, anyway, you understand what I mean. Yeah. because fermion chemical potential now is negative. So it could be negative. So anyway, this should be plus, I think. Yeah. Anyway, so then I use this effective 2-channel model to study the many-body properties, and we compare the results with a single-channel model. So the solid line is from our 2-channel model, and the dotted line is from a single-channel model. The single-channel model is that you basically project everything to the ground state. And this is a number distribution within a trap. So you can see there's a sizable difference. And now I go to the final thing, is the validity of a contact interaction. So you can see all my discussion above heavily relies on the use of the contact interaction. The many-body thing is, because the contact interaction is so simple and has some nice properties, we cannot, we cannot reject the attempt to use it. But the question is that can we still use it in the presence of spin-orbit coupling? Okay? So in order to answer that question, we will study the 2-body scattering problem in both 2-dimensional or quasi-2-dimensional. So we assume that the interaction is not a delta function, is actually a short-range interaction. And then we calculate the 2-dimensional scattering amplitude like this, where the A function is something like this. And as you can see, the scattering amplitude right now is dependent on the center of mass momentum. This is because the spin-orbit coupling is not, yes?
Could you explain your notation? On the left, you have a number or a function, and on the right, you have a bra. What does this mean?
I think it's dimensional.
I just don't understand.
There's no bra. I mean, this one, this together is a bra. This is in the this is momentum, and this is let me see. This is spin. Yes. So the two bra together make a bra.
Okay, that's like a direct product.
Yes. 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 So and let me see. Yes, and the first three terms in the denominator is present when there is no spin orbit coupling, and the final term, which is the lambda function, is the effect of spin orbit coupling. So as you can see, this scattering amplitude is definitely Q dependent, and the low energy limit of this scattering amplitude is also changed. Without spin orbit coupling, this term is not present. So the scattering amplitude is logarithmically divergent. But in the presence of spin orbit coupling, this term actually gives you the leading divergence. So the scattering amplitude is power law divergent. And this is the difference. So you see when there is no spin orbit coupling, it's logarithmically divergent. But when there is a spin orbit coupling, it becomes a linear line here. But this is not quite linear, but yeah, you can see from here. Okay, and then we do the same thing, but in quasi-two-dimensional case. And in this case, we assume a three-dimensional isotropic short-range interaction. And now we add an interaction confinement along the z direction.
Can you separate the center of mass and relative momentum in this case?
No, but what you need to do is you need to do everything for a specific center of mass momentum.
So
as long as you do that, you can separate.
I mean at the initial asymptotic state, is because the center of mass momentum is not conserved in this case.
The initial one, yes.
So you define the
initial one.
State, you see, with a certain center of mass.
Yes.
But then the center of mass changes.
Yes. 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 Okay. And then you see in the quasi-2D case, the A function transform like this. If you compare with the pure 2D case, you can see the only difference is that the D here is replaced by some D effective, which depends on the scattering energy and the center of mass momentum. Okay, so then with that calculation, we can write down an effective Hamiltonian. Around threshold, the effective Hamiltonian has a single channel model form because this is around threshold, so the excited states are not significantly populated. But as you can see, we can still use a contact interaction form, but at this time, the contact interaction has some center of mass momentum dependent. This G of Q is the contact interaction, and it is determined by this equation.
Is that K plus K double prime? And the third A, the third operator.
This one?
K plus
yes, K plus K double prime. Yes.
So
yes.
you still have momentum conservation.
Yes. Yeah, we always have momentum conservation. Yes.
And what does the prime mean to the left of G?
This one? Oh, the G. The prime is come to the summation.
Do you exclude some term in the sum?
Let me see.
It's a funny interaction.
I can't remember because I really sorry I can't remember the prime come from, but it's associated with the summation. You probably refine to some part of the momentum space. Yeah, sorry.
The initial center of mass momentum is K plus K prime.
Yes.
Finally, it's 2K prime.
No, this is a typo. This should be K. One of these should be K. This is K plus K double prime, and this is K prime minus the double prime. It's a typo. Yeah.
But then it means that your interaction can serve the center of mass
maybe
momentum.
you can
Let me
try to wrap it up.
let me finish.
Okay.
Because you see, we agree that the center of mass momentum is not conserved, but then you see, if you write as you say, then the center of mass momentum is conserved. So So there is a contradiction between what you said earlier and what you have now.
We can have the discussion in the afternoon.
Okay.
There's no discussion, there's a question.
Okay. Yeah. Wait, okay. So here I assume a contact interaction. So we basically don't care what happens inside. So what I say is that we have two incident particles. There's a center of mass momentum, and then it's scattered away. You have another center of mass momentum. It is conserved. Then it is conserved.
If you have spin-orbit interaction, it's not.
No, it is conserved. It is when you have spin-orbit coupling. It is not conserved when you have interaction. But when it's scattered away, it is conserved. Well, yeah, we can hold that in the interaction, but I'm not sure I quite understand your question anyway. Yeah. So then if you do that around the two-body binding energy, then you can also the effective Hamiltonian takes a two-channel model form, but again, every parameter here you can see the V of Q, the detuning, and the molecule to fermion coupling is still the Q dependent. Okay, and so this is the I think this is the conclusion, is that contact interaction is valid provided that the interaction is short range, the SOC intensity is weak, and the effective contact interaction strength is Q dependent. So we need to include Q dependency into the interaction strength. And I will stop here. Thank you for your attention.
Thank you very much. Just one question, yeah. Other questions can be postponed to the afternoon. Yeah. We're out of time, sorry. Okay.
I thought this separability, the way it worked was, although I haven't looked too much at the Rashba case, was that it is separable, but the relative part of the Hamiltonian depends on the center of mass.
Yes. Yes.
So it is separable, but it's not as separated as it often is.
Yes, yes. That was said. You have to, given a center of mass momentum, then it is then your relative Hamiltonian does not depend on that.
You still have the momentum conservation, but you break the Galilean symmetry.
That's right.
Let's thank the speaker again.
Okay.
We'll gather at the elevator for lunch at 12:30. And